Hello everyone. Welcome to my online video lecture series on Introduction to the Finite Element Method. Let me start by introducing myself. My name is Siddhesh Sakharkar. I have a PhD in mechanical engineering from UC Berkeley, and I currently work as a mechanical simulation engineer in the industry where I use the finite element method to solve real-world problems. The goal of this video lecture series is to provide you with a brief overview of how the finite element method works in 1D. Specifically, our objective is to solve the Poisson's equation in 1D using linear finite elements. In each video lecture, I will discuss the key concepts involved in the finite element method, and in the last lecture, I will also share a Python code that implements these concepts in order to solve the Poisson's equation using the finite element method. The reference textbook for this video lecture series is a book called The Finite Element Method by Professor Hughes. So if you're interested in more details, I would definitely recommend checking out this textbook. So let's get started. So let's start by writing out the Poisson's equation in 1D. The Poisson's equation is given by the second derivative of u with respect to x plus some function f of x is equal to 0. Here u of x is the unknown solution that we want to solve for, and f of x is some predefined function. For simplicity, we consider the domain x belonging to 0 to 1. Now this differential equation by itself is going to have an infinite number of solutions. In order to define a unique solution, we need to specify boundary conditions at the boundaries, that is at x equal to 0 and x equal to 1. At x equal to 0, we consider a Neumann boundary condition where we apply a constraint to the derivative of u with respect to x. This boundary condition can be written as minus du by dx at x equal to 0 is equal to some constant h. So this right here is our Neumann boundary condition. At x equal to 1, we consider a Dirichlet boundary condition where we apply a constraint to the solution u at x equal to 1. So this boundary condition can be written as u of 1 is equal to some constant g. So this right here is our Dirichlet boundary condition. So the differential equation coupled with these two boundary conditions together form the strong form S of the boundary value problem, that is the Poisson's equation. The finite element method is based on the discretization of the weak form of the boundary value problem, and in today's video lecture we are going to discuss how do we derive the weak form from the strong form. To derive the weak form, we begin by considering a test function w of x. We multiply the differential equation with this test function, so that gives us w of x multiplied by d2u by dx square plus f of x, and then we integrate this across the domain, that is from 0 to 1 dx. Now since d2u by dx square plus f of x is equal to 0 by our differential equation, this integral should also be equal to 0 for all functions w of x. Now in general, w of x could be any arbitrary function, but additionally we apply a constraint to w of x such that w of 1 is equal to 0. Now the reason for specifying the constraint that w of 1 has to be equal to 0 is that at x equal to 1, we have a Dirichlet boundary condition which states that u of 1 has to be equal to a constant g. So basically, wherever on the boundary a Dirichlet boundary condition has been defined for the solution, we require that w of x should also vanish at that particular location. Now to simplify this particular integral, we use integration by parts. Now I personally always struggle to remember the formula for integration by parts, and hence I prefer to derive it from scratch using the product rule. So here's how we do that. We begin by considering the expression d by dx of w multiplied by du by dx. It will be clear in a minute why I'm considering this particular expression. But let's now evaluate it. So using the product rule, this can be expressed as w multiplied by d2u by dx square plus dw by dx multiplied by du by dx. Now this term over here is the same as this term over here, and that's the reason why I started with this particular expression. We now integrate this across the domain, and now this can be written as integral 0 to 1. Let's start by considering this term. So it can be written as w multiplied by d2u by dx square dx is equal to integral 0 to 1 d by dx of w multiplied by du by dx minus integral 0 to 1 dw by dx du by dx. Now the first term here can be directly integrated to be written as w multiplied by du by dx evaluated at 0 and 1, and the second term remains as it is, integral 0 to 1 dw by dx du by dx. Now we know that at x equal to 1, w of 1 has been specified to be equal to 0, and so the first term is going to vanish and the only term remaining will be minus w of 0 multiplied by du by dx evaluated at x equal to 0. Further, by the Neumann boundary condition, we know that at x equal to 0, minus du by dx is equal to a constant h. Using that, the first term over here can be written as w of 0 multiplied by a constant h, and the second term remains as it is, integral 0 to 1 dw by dx du by dx. Now we insert this expression back into the integral equation, and that gives us integral 0 to 1 dw by dx du by dx with the negative sign plus integral 0 to 1 w multiplied by f dx, which is this term over here, plus w of 0 multiplied by h has to be equal to 0. Now this equation right here is called the weak form of the boundary value problem. In this equation, for this integral to be finite, we require that the test function w and the trial solution u should both be something called h1 functions or belong to an h1 function space. Now what does that mean? W being an h1 function means that if we consider the integral of the first derivative of w with respect to x squared across the domain 0 to 1, then this integral should be finite. So basically it should be less than infinity. By requiring that both w and u are h1 functions, we essentially ensure that this integral right here is finite. Now in order to formally specify the weak form, we need to define a few function spaces. So let's see how that works. We begin by defining a trial solution space S, which is the set of all functions u, such that u is an h1 function, which we just defined, and u satisfies the Dirichlet boundary condition, that is, u of 1 is equal to a constant g. Secondly, we define a function space of test functions t, which is the set of all functions w, such that w is an h1 function and w of 1 is equal to 0. Now we can formally state the weak form of the boundary value problem as, given a function f of x and given some constants g and h, find a function u which belongs to the solution function space S that we have just defined over here, such that the following equation holds true. The equation is given by integral 0 to 1 dw by dx du by dx is equal to integral 0 to 1 w f dx plus w of 0 times h. And this equation must hold true for all functions w belonging to the test function space T. So this right here is the formal definition of the weak form W of the boundary value problem. So what we have just shown is that if we start from the strong form, we can show that the weak form should also be true. So basically the strong form implies the weak form. Now why is this called the weak form and what we started with called the strong form? So if you look at the strong form of the boundary value problem, you'll notice that it involves the second derivative of u with respect to x. On the other hand, if we look at the weak form, then you'll notice that it only involves the first derivative of u with respect to x. Now when we use the finite element method to solve a problem, we are looking for an approximate solution u that satisfies the Poisson's equation. So if our approximate solution is based on the strong form, then we would require the second derivative of the approximate solution to be well defined for the Poisson's equation to be satisfied. On the other hand, if our method is based on the weak form, then it is sufficient for just the first derivative to be well defined and it is still possible to satisfy the weak form. Thus, with the weak form, we have weakened the requirement for the derivative of the approximate solution from the strong form, and this is why it is called the weak form. Now, with this derivation, we have shown that the strong form implies the weak form, but what's interesting is that the opposite relation also holds true. So if we start with the weak form and assume that it is true, then it is possible to show that the strong form should also be true. Now this is important to note that both the strong form and the weak form are equally valid and they are equivalent. And so the weak form is only called weak because we have weakened the requirement for the derivative and it has nothing to do with how valid the form is. Now let's start by showing you how, starting from the weak form, we can derive that the strong form should also be true. Let's start by writing out the weak form. So the weak form is given by integral 0 to 1 dw by dx du by dx is equal to integral 0 to 1 w multiplied by f dx plus w of 0 multiplied by h. To get back to the strong form, we are again going to integrate by parts and essentially follow back the steps that we just used to derive the weak form from the strong form. When we do that, what we get is as follows. Integral 0 to 1 w multiplied by d2u by dx square plus f dx plus w of 0 multiplied by du by dx at x equal to 0 plus h is equal to 0. Now how did I get this? So when we start from the weak form and integrate by parts and follow back the steps, then we'll get this equation over here, which is the same as the first term over here. But why do we have this extra second term? So when we started from the strong form and then derived the weak form, if you remember, we used the relation that minus du by dx evaluated at x equal to 0 is equal to h, which is basically our Neumann boundary condition. And hence we have this extra term over here. Now, in order to derive the strong form, we need to show three parts are true. So the strong form has three parts. Firstly, we have the differential equation over here. Next, we have the Neumann boundary condition. And thirdly, we have the Dirichlet boundary condition. Now, by assuming that u belongs to the solution function space, we already assume that the Dirichlet boundary condition is true. So we already know that u of 1 is equal to g. So all that we need to show is that the Neumann boundary condition is true and the differential equation is true. So if you notice, the first term over here is the Poisson's differential equation, whereas the second term over here is the Neumann boundary condition. So to show that the strong form is true, we need to show that both these terms over here are equal to 0. To show that, let's now consider a special case of w of x. Now we know that this equation over here must be true for any function w of x. So we consider a special case where w of x is given by some function, is given by some function phi of x multiplied by d2u by dx square plus f of x, where phi of x is some function which satisfies phi of x is greater than 0 for x belonging to the domain, that is from 0 to 1, and phi of x is equal to 0 at the boundaries. Basically, phi of x is some function which looks like this. At 0 and 1 it is equal to 0, and in between it is positive. Now it will be clear in a minute why I chose this particular form of w of x. For now, let's substitute this w of x into this equation over here and see what we get. So the first term can be written as integral 0 to 1 phi multiplied by d2u by dx square plus f squared dx. Now w of x contains this term over here, which when multiplied by the same term gives the square of that particular term, and this is the reason why I chose this particular form of w of x. Regarding the second term, it involves w of 0, but we know that phi of 0 is equal to 0, and hence w of 0 for this particular w has to be equal to 0, and so the second term is equal to 0, and this is equal to 0. Now we know that the function phi is greater than 0 within the domain, that is within 0 to 1, whereas this term over here, which is a square, must also be greater than or equal to 0. With this in mind, the only way this integral can be equal to 0 is if the term d2u by dx square plus f is identically equal to 0 for x belonging to 0 to 1. Now why is that true? Let's say there is some interval delta within 0 to 1 in which d2u by dx square plus f of x is not equal to 0, and this term is equal to 0 everywhere outside of delta. Now within delta, we know that d2u by dx square plus f is not equal to 0, and hence its square, that is this term over here, must be greater than 0 or strictly positive. We already know that phi is greater than 0, and hence the product of these two terms must be greater than 0 within delta, and hence its integral should also be greater than 0 within delta. But outside delta, we assume that this term over here is 0, and hence this integral is 0 outside delta, and hence overall across the domain 0 to 1, this integral must be greater than 0 or positive. But that's a contradiction because we know that the integral must be equal to 0. That means that there can be no such interval delta within which d2u by dx square plus f of x is not equal to 0, and so that means that this term over here must be identically equal to 0 for x belonging to the entire domain, that is 0 to 1. Now when we substitute this particular equation into this integral equation over here, the first term is going to vanish, and all we are left with is that w of 0 multiplied by du by dx evaluated at x equal to 0 plus h is equal to 0. Now we know that this must hold true for all functions w belonging to the test function space. So now we consider a special case w of x which belongs to the test function space such that w of 0 is not equal to 0. Now with that in mind, this equation is true means that du by dx evaluated at x equal to 0 must be equal to minus h, which is our Neumann boundary condition. So we have now shown that the Poisson's equation, that is the differential equation, must be true. The Neumann equation, the Neumann boundary condition is already true. And with the weak form, we assume that U belongs to the solution function space, and so U of 1 is equal to G. So the Dirichlet boundary condition is already assumed to be true. Thus, by starting from the weak form, we have now shown that all three parts of the strong form, that is the strong form of the boundary value problem, is also true. In summary, we have shown that not only does the strong form imply the weak form, but the weak form also implies the strong form. As I mentioned previously, the finite element method is based on the discretization of the weak form of the boundary value problem. I'll show you how to do that in our next lecture. Thank you for listening, and I hope you learned something.